All right, let me grab this and start the recording and do this. Awesome. Okay, here we go. Julia, can you do me a big favor? I can't actually see this chat screen. Actually, you know what? I can move it so that I can. Hold on 1 second. Okay, let's see. Conferencing. This right here. This right here. Options that. Make this size 16. There we go. Awesome. Cool. Okay. Let's do this. All right. This is kind of off the top of my head. We'll see where we go with this. We'll see how far I can do this. All right. What I've covered with you so far is work is equal to force times distance. And the idea behind this is the force is actually measured in newtons, and this is units. The force is measured in newtons, the distance is measured in meters. So you have a newton times a meters. We named this after this dude named Joules, and so that's also known as a joules. That's what force times distance is. That's what work is measured in. Hey, where's my cloth that I need? Hold on 1 second. Where is my, oh, there it is. Got it, I see it. All right, so work equals force times distance. Joules is the same as newton meters. Another way to play with the units would be kilograms, meters per second squared times meters is the same as joules. Do you see how that newtons actually just changed over to kilogram meters per second squared? Do you guys see that? Yes, no? Because a newton is a force, and a force is equal to mass times acceleration. Kilograms is mass, and acceleration is meter per second squared. So it's also known as a kilogram meter squared per second squared. I'm just looking at just the units here. Am I freaking anybody out yet? No. Yes. Maybe. Are you guys chatting back with me? I can't tell.
No, you can.
Oh, okay. Did you guys say something and I just can't see it? Try chatting back and say hello or something like that. Okay, there, I can see you. All right, good. You guys just weren't talking to me. All right. I introduced you this concept of, all right, let's go through some more equations. I introduced you the concept of kinetic energy, which is 1/2 mv squared. Now, I denote that with a KE, and I say, all right, the kinetic energy is mass times velocity squared. Does that make sense? Oh, by the way, I'm sorry. This is joules, which is the same as kilogram meter squared per second squared, which is also the same as newton meters. I can play with this thing all day. That's how I would get it. This thing right here, kinetic energy is 1/2 mv squared. Where does this m come from? Well, the m comes from, I mean, imagine if you can think about it like, when I think of energy and work, I think of pain. So, if I'm playing football, and I've got somebody running at me full on, like running at me, like they're like, ah! And they're like foaming at the mouth and whatever, then I would be more afraid of a 200-pound man versus a 100-pound man. Would you guys agree? Like, I would be more afraid to be hit by Dustin, the 6th grade teacher at the school, who's a rugby player, used to weigh 280 pounds, versus being tackled by a Julia, who, sorry Julia, I know that you're tough, I'm just saying, I'd rather not be tackled by the 280-pound rugby player. Would you agree? Yes, of course you agree. Well, that makes sense. Yeah, exactly, there we go. So mass has something to do with it. I also would be more afraid if Dustin were running with a high velocity than a low velocity. So that's why kinetic energy relates to this thing. It would cause more pain if the velocity increased. All right. Let's check the units to make sure that this equation actually is a valid one. This m over here is measured in kilograms. This v over here is measured in meters per second. But I square that sucker, and I end up getting meters squared per second squared. Oh, the 1/2 doesn't contribute any units to it whatsoever. So, can you see how this expression right here is really an expression for energy? Work equals force times distance. Are we cool? Awesome. There's another equation that I gave you. Let's do this one. Potential energy. I don't know if I've covered this with you yet, but let's talk about this one. The potential energy. What would you use to define the word potential? If I ask you, what does potential mean? How would you define it? The ability to do something, exactly. So maybe let's say potential energy in terms of our pain exercise is the ability to cause pain. So where's my weight that I had? I had a weight over here and I was dropping it on my head and it was really sore. Let's do this. Okay, hold on 1 second. Let's find something to drop on my head. Hold on, there we go. Not CD. 1 second. Okay, wait, I'll grab something else.
And just one pH, value of pH change is going to have a huge impact. Okay? So, here's the formulas. I actually put these formulas on your lab document that you need to keep in mind. So, carbon dioxide. Lots of carbon dioxide.
Okay, alright, I got it. Okay, so check this out.
What is, carbon dioxide?
Whew. Alright. Potential energy. The ability to do something. If I have something that has a small mass, I put it over my head, okay? And I drop it. Ow. That kind of hurt. Actually, it hurt yesterday when I dropped a 2 kilogram mass, like a steel mass on my head, to show Julia. Actually, I think that was Wednesday. But that's not so bad. However, if I take this 25-pound weight and I put it over my head and I drop it, which would you be more afraid of? Which would have the ability to cause more pain? This thing or this thing? Come on, talk to me, interact with me. The heavier mass, exactly. So the amount of potential energy is dependent on the mass. And the reason why I say which one would cause more pain is because I want to know whether or not it's directly proportional or indirectly proportional. If it's directly proportional, then it goes in the numerator. If it's indirectly proportional, it goes in the denominator, or I make it 1 over, that number. What I mean by indirectly proportional is if maybe the weight increased but the pain decreased. You know what I mean? This obviously is directly, so it would go in the numerator. Alright, now I got a question. Which scenario would you say has the ability to cause more pain? Here or here? Scenario 1 or scenario 2? I'm going to break this piece of glass in front of me. I'm just going to drop it and it's going to break and shatter the glass, I bet you. Scenario 2, exactly. Scenario 2, what did I change? I didn't change the mass, but what I did was I changed the distance. Now I don't want to say distance specifically because, alright, let's talk about distance. Okay? If I have it here and I move it a distance, I move it a distance maybe this far, will it cause any more or less pain versus move it a distance? Does this make sense to you? What I mean by distance is I don't want to say distance, because distance just kind of implies like any kind of movement. No, not displacement. What I mean by it is my potential energy is dependent on a very specific type of distance, is dependent on height. It's dependent on the vertical distance. Because moving it horizontally won't really change the amount of energy that I'm giving it, right? Right, exactly. Because moving it horizontal or moving it vertically changes where it's placed in the gravitational field, something like that. What is the last thing that potential energy must be related to? The amount of pain that is induced. And you have it in the sentence that you wrote back to me, that word you have. What does that say?
On the far left here, you have a
Gravity. Think about it like this. If I'm holding that weight above my head on Earth and I drop it, that would be soared. If I'm holding that weight above my head on the moon and I drop it, will that be as soared? And Julia, please talk back with me. Use your microphone. The other two girls, you can talk back. I'd love to hear your voice. Or what you'll probably have to do is just type back. What is, if I had it on the moon, would it hurt as much? Would it have the ability to cause more pain? Greater gravity, greater potential energy. I like the way you said that. Exactly. If I'm talking about, if I increase the amount of gravity, then I'm increasing the amount of pain that it could cause. On the moon, it has less gravity, so the pain that you would experience is less. Versus if you put it on Jupiter, which is 16 times the amount of gravity, that thing would kill you. I mean, I wouldn't necessarily say you'd be very safe when you do it on Earth. But, you know, I mean. All right, Catherine, I think what you're trying to do is, how do you see the video and chat at the same time? I think you made the video full screen. Whereas, as opposed to making it like that little, really small screen, what you might want to do is take that screen, the really small screen, and drag it so that it's proportionally big. And then you can chat and see the video at the same time. All right, so potential energy is a measurement of gravity. Let's check the units on that. Gravity is measured in meters per second squared. Mass is measured in kilograms, and height is measured in meters. So the units for potential energy is meters squared per second squared times kilograms. Hey, wait a second, that's still a joules. So we're in the clear here. Do you see how all of this? Do you see how all of these equations are? I mean, kind of these equations have the same units.
So what we're going to do is we're going to measure these.
All right.
We are going to take
Okay, so here's what I'm going to do. I'm going to do one more because I feel like this one's a little bit more obscure, and I don't know why I taught this to you earlier. I actually just was following the book, but then I'm looking at this, and I thought to myself, I'd rather just kind of like talk to you about the whole thing as opposed to just follow the book. So here's me talking to you about the whole thing. Let's take a look at this one. A spring has a force related to it. That force is K times X. I taught this to Julia and I recorded some videos, so I'm not going to go too deep into this, but I will tell you what the measurement of K is. K is measured in newtons divided by meters. Are we cool with that? Okay. Because X is measured in meters. So if K is measured in newtons per meters, then when you multiply this times a meters, you end up getting newtons, which is what a force is supposed to be measured in anyway. All right, let's keep that in mind. What I can talk about now is I can also talk about the amount of potential energy in a spring. What I do sometimes when I teach physics is I hold a bow and arrow up in class, but I didn't bring my bow and arrow today because I couldn't carry it on the bus. I'm serious, this is what I do. I pulled back the bow and arrow, and I pointed at someone's face. Hint, hint, it's not loaded. But people get really scared. And I say, how much energy, or how much potential energy does this thing have? Because it has potential energy. It's not hurting you yet, but it can hurt you, right? So it is a form of potential energy. It just happens to be energy that's stored in some kind of rubbery thing, like the bows of a bow and arrow, or the rubber band, or a spring, or some kind of elastic thing. Am I making sense here? So this is a different form of potential energy. Sometimes what I like to do is I like to call it potential energy with a little s on the bottom of it, as opposed to potential energy as attributed from gravity, which I like to call PE with a little g on the bottom of it. We cool? Have I lost anybody here? Now the potential energy in a spring, I'll give you the equation for it. It's 1/2 kx squared. Let's check this to make sure that it's got the right units for it. The k is measured in newtons per meter. The x squared is measured in meters squared. One of these meters on the bottom cancels out with one of those on the top, and you end up getting newton meters, which is the same as a joules. We're good with this equation. Okay? But this is the spring energy that you get. Now, when do you use this? How do you use this? Well, I'll show you in example problems. But these are pretty much the three forms of mechanical energy that I can tell you about. This is all of the stuff that we need to cover. And I believe that I only introduced to you maybe these two in the first chapter and then this one in the second chapter, and I think that that was a mistake. I should have just kind of introduced to you the whole concept as a whole altogether. Now, let's talk about how we want to use this stuff and maybe how to apply these equations. And then what I'll do is I'll do some really fun things where I'm going to have like an iron close to my face, and then we're going to drop it and make it swing and all of that kind of stuff. It's going to be a lot of fun. I'm going to erase this. So I've given you 4 equations to work with here. Work equals force times distance. Kinetic energy is 1/2 mv squared. Potential energy is mgh. And spring potential energy is 1/2 kx squared. How would I use this on a pendulum? Here's the really awesome thing about energy. I froze. Am I still there? Julia, can you not hear me? Oh, shoot. Okay. Julia, 1 second.